You remember last week we were talking about how to solve quantum mechanics problems in 3 dimensions, right? And we did one example of a particle in a 3D rectangular box. And so that worked fine using a method that was kind of a generalization of what we did in 1 dimension. But then what I tried to point out to you at the end of the class is that this works for a particular kind of potential energy that has a simple form in Cartesian coordinates. But most kinds of potential energy are not so simple in Cartesian coordinates. And so, in that case, we wouldn't be able to use that method to get an exact solution. Right, so we need to do something a little different if we want to have any hope of getting an exact solution. And so, what we do, well, of course, it depends on what the potential energy is in any specific problem. But there are a lot of problems where the potential energy depends on the distance out from the origin and not on the direction. Right, where the potential energy has a spherical symmetry, that the only thing that matters is the distance from the center. Right? For example, if an electron feels the Coulomb attraction toward a proton, right, then the potential energy for the electron depends on the distance from the proton, but it doesn't depend on the direction. Right? And so that's a big class of problems that are like that, where the potential energy only depends on the distance from the origin and nothing else. So whenever you have a problem like that, it's convenient to work in spherical coordinates. That is the coordinate system that's indicated here, where one of the coordinates is the distance out from the center, and the other two are these 2 angles, the angle down from the z-axis and the angle going around from the x-axis. And if we do that, then the potential energy only depends on one of these variables. Which is just this r variable, the distance out from the origin. Okay, so it makes a big simplification in the potential energy. That's good. Now, you pay a price for that. Okay, you pay a price that other things are less simple. There are lots of expressions for the derivatives and integrals, which I'll show you in a minute, which are less simple than if you're in Cartesian coordinates. The claim is it's worth it, right? That it's worth making those other things more complicated in order to make the potential energy simpler. Okay, so let me show you how to do it. Okay, so the coordinate system is sketched here, right? This is my picture from last week. And so here you can see that any particular point could be described in Cartesian coordinates as x, y, and z, or it can be described in spherical coordinates by r, the distance out from the origin, and theta, the angle down from the z-axis, so that's like 90 degrees minus latitude on the globe. And then the azimuthal angle phi, that is, if you take the vector from the origin to the point in question and you project that down into the xy plane, that vector has an orientation phi with respect to the x-axis. Okay, so based on this, we can do a little bit of trigonometry to relate the coordinates x, y, and z to the coordinates r, theta, and phi. Right? So the relation, which you hopefully have seen in a math class, looks like this, right? That x is equal to r sine theta cosine phi, y is r sine theta sine phi, and z is r cosine theta. And then if you take those expressions and you add up x squared plus y squared plus z squared, you get that that's equal to r squared. And so this is the, the Pythagorean theorem for the distance that a point is out from the origin. So are these expressions sort of familiar to you guys from math classes? Yes, you did get these in the math methods for physics. Excellent, excellent. Okay, and so that means that instead of having a wave function that's a function of x, y, z, and time, now we're going to have a function of r, theta, phi, and time. All right, so this is the new thing that we want to solve for, right? That if we're doing a problem in spherical coordinates, we want to solve for what is the psi as a function of those four variables, r, theta, phi, and time. Okay, now when we're doing that, we can do all the same interpretation of the wave function, right? And so we could say, how do we do integrals to normalize the wave function, for example? Right, so say how to do integrals. Well, here we need to integrate over these three variables, right? R, theta, phi in spherical coordinates. Okay? So when we do the integrals, we want to integrate r from the minimum value, which is 0, up to the maximum value, infinity. And the integral has a factor of r squared times dr. And this factor, r squared, is a part of what's called the measure of integration. That is, it describes if you have a little interval of r, how much volume is covered by that interval. Right? And so if it's a little interval, just, 1 centimeter of r near the origin, that covers a little bit of volume. If it's 1 centimeter of r far from the origin, it covers some great big interval of volume, a much bigger interval. And so it's important to have that factor of r squared. Okay? Likewise, now we have to integrate over theta. And we do that by integrating from the North Pole, where theta is 0, to the South Pole, where theta is pi. And the measure of integration has a factor of sine theta times d theta. Okay? For the same reason that there's a factor of r squared. That is, if you have a little interval of, say, 1 degree of latitude, near the North Pole, that covers a small amount of territory. If we have 1 degree of latitude near the equator, that covers a big belt all the way around the equator, right? That covers a lot of territory. And this factor of sine theta shows that dependence. All right. And then we have to integrate over phi. And so that is going from 0 to 2 pi. That is the full range of phi, say from the prime meridian of longitude all around the globe back to the prime meridian. And there is no extra factor there because every interval of phi covers the same amount of territory. Okay, so whatever we are going to integrate, put it symbolized by all these dots, we have to integrate it in this way. That is, we integrate over those 3 variables, r, theta, and phi, with the factor of r squared sine theta as the measure of integration. Okay. Now, because this is a lot of writing for how to do the integral, people often write it in a slightly shorter way as just the integral r squared sine theta dr d theta d phi of whatever goes there. Okay. And so here, this is just a shorter way of writing, which saves space and time by only putting one integral sign there and leaving off the limits of integration. Okay, but don't let it fool you. This is still a definite integral, and it's a definite integral over these limits. Okay, so this is the sort of arrogant notation that, I know what I mean, and I'll just assume everybody knows what I mean, so I don't have to actually write what I mean. Okay, and so this is a shorthand for all of that stuff. Okay. And again, here is the measure of integration, and you absolutely need to include the factors of r squared and sine theta, or you are guaranteed to get the wrong answer. Okay, so that is how to do derivatives, excuse me, that is how to do integrals in spherical coordinates. And it's complicated. Well, it's more complicated than Cartesian coordinates. It's not that complicated, but it's more complicated than Cartesian coordinates because the change in r or a change in theta, it covers different distances in 3D space. It covers different amounts of territory depending on where you're located. Now, what about derivatives? Okay, so we'll say how to do derivatives. Okay. So, in 3 dimensions, we have all these vector derivative operators like the gradient and the divergence and the curl and the Laplacian, right? So all of these things are a little bit different in spherical coordinates than they are in Cartesian coordinates. And so I'll show you what the rules are. Okay, so if you want to say the gradient of a scalar, so gradient of a scalar, so if we have f of r, theta, and phi, okay, then the gradient of f is equal to the partial of f with respect to r in the r hat direction. plus 1 over r partial f partial theta in the theta hat direction, plus 1 over r sine theta in times the partial f partial phi in the phi hat direction. So, it's not just these factors of df dr, df d theta, df d phi. Rather, you need these extra factors, 1 over r, 1 over r sine theta, right, in order to make the gradient come out right, in order to make it come out consistent with the way it's defined in Cartesian coordinates. Right? What if we want the divergence of a vector field? So if there's some vector A as a function of r, theta, and phi, and we want the divergence of A, let's see, that is equal to, I'll have to copy this one from my notes, 1 over r squared d by dr of r squared a sub r plus 1 over r sine theta d by d theta of sine theta a sub theta plus 1 over r sine theta d by d phi of a sub phi, okay, where a sub r, a sub theta, and a sub phi are the 3 components of the vector A in spherical coordinates. Okay, and then what if you want the Laplacian of a scalar? So, we have talked last week about the Laplacian operator, that shows up in Schrodinger's equation, and that is equal to the divergence of the gradient of f. So we can get it by combining the 2 equations up here and there, right? So if we do that combination, here, I'll skip to the answer. If we do that combination, we get 1 over r squared d by dr of r squared df dr plus 1 over r squared sine theta d by d theta of sine theta df d theta, and 1 over r squared sine theta, no, sine squared theta, excuse me, then the second derivative, d2f d phi squared, like that. Okay, and so, these are the rules for taking any of these vector operators, the vector derivative operators in spherical coordinates. And these rules are necessary, well, for 2 reasons, right? One is because of what I told you before with integrals, right? That a little change in r or theta covers a different amount of territory depending on where you're located. That's one reason. And the other reason is that the characteristic directions, r going out from the origin and theta hat going down from the North Pole and phi hat going around the z-axis, those unit vectors change depending on where you're located. Right? That these things are not constants, right? R over here is pointing this way. Over here, our head is pointing that way. Over here, it's pointing that way, right? And so you can't regard those unit vectors as constants the way you can regard x hat and y hat and z hat as constants. Okay, so I'm not deriving these expressions. I'm just telling you, but perhaps you saw these derived already in a math class. Did you already see these derived in a math class? These kinds of relations? Or were they just told to you in a math class and not derived?
It's been a while, to be very honest with you.
It's been a while. Okay, fair enough. Yeah, well, I mean,
I want to say yes, they derived it, but it's been a hot minute.
yeah, I mean, I could derive them, but it would take an hour or so to go through all these things, and it wouldn't be the most interesting hour. So maybe I'll skip on that. When I was a student, I would always remind myself of these relations because they were printed in the inside cover of some of my textbooks. That's kind of an old-fashioned idea, right? You probably don't have textbooks with covers anymore, but they're on lots of websites and they're built into software like Mathematica, all of these relations, right? So whenever you say, take the Laplacian in Mathematica, you have to tell Mathematica which coordinate system you're working in. Is it Cartesian or spherical? And then it knows about coordinate systems and it does the right thing in the coordinate system that you tell it. Okay, so let's maybe believe these relations rather than trying to go back and derive them. Okay, and see what they mean for Schrodinger's equation. Okay, so suppose we want to solve Schrodinger's equation in in spherical coordinates. Okay, so for the Schrodinger equation in spherical coordinates. So we have that I h bar, the derivative with respect to time of psi, which is a function of r, theta, phi, and t. Right, the partial derivative of that with respect to t. That is equal to minus h bar squared over 2m times the Laplacian of psi plus the potential energy times psi. Okay. And when I write this, let's point out that this Laplacian, this is the Laplacian in spherical coordinates. I'm not writing it all out just right now to save time, but I will again in a minute, okay? But this Laplacian means the same thing that's written out all of here, but with that f is changed to psi. Okay. And then that's the bad news, right? The good news is that the potential energy, let's say that's just a function of r, and it doesn't depend on theta or phi or time. Okay, so now we want to solve this. Okay, so let's do this work first to separate out time from the other position variables. Okay, so if we do separation of variables, okay, so the first step is the same as always, to say that psi of r theta phi and time is some time independent thing times e to the minus I energy time over h bar. Right? This always works, okay, in any coordinate system. And if we have that, then this gives us that the time independent Schrodinger equation. Which is that the negative h bar squared over 2m Laplacian of psi plus v psi is equal to e psi. This always works, right? So this is just repeating the steps that we have had before. And here I, of course, meant to write lowercase size. Excuse me about that. Lowercase r theta phi v of r e, oops, times psi of r theta phi. Okay, this is what we want to do. This is what we want to solve. Okay, now let's do something that's different in spherical coordinates. Okay, so we have this time independent Schrodinger equation. Now let's do separation of variables again. Right? So let's suppose that this psi that depends on the three variables in spherical coordinates, let's suppose that this is one function of r times another function y of theta and phi. I'll keep the theta and phi together. I won't separate those, but no, I could, but I won't. Okay, so now we want to put this assumption into the time independent Schrodinger equation. So now negative h bar squared over 2m. Now I need here, actually got to do it. I've got to write out what is this Laplacian in spherical coordinates, okay? And then try to simplify that. So the first term, is 1 over r squared d by dr of r squared times d by dr of the function, okay? The function now is capital R times y. Okay? The y is a constant as far as all of this R derivative stuff goes. So I can factor it out. Okay, so let's just put the y way out in the front, and we just have a derivative of capital R. Okay, now the next term is plus 1 over little r squared sine theta d by d theta times sine theta d by d theta of the function, okay? But the function now is capital R times capital Y. Right? Capital R is a constant as far as theta is concerned. So it just factors out like that. And we only need to have a derivative of Y in here. Okay, now the third term. This is plus 1 over R squared sine squared theta. And then we have the second derivative with respect to phi of the function. But once again, the function is capital R times Y, and capital R is a constant as far as phi is concerned. So it factors out like this, and we just need the derivatives with respect to the derivatives of Y with respect to phi. Okay, now that's the Laplacian term. Then we have to add on V of R, the potential energy, times capital R of R, times Y of theta and phi. And all of this is equal to the energy times capital R times Y of theta and phi. Okay, are we good so far? All right, there's nothing in the chat. I never see the chat. I never see the chat. Okay. Here, more chat. Oh, okay, there was an old chat. Okay, good. Thank you, Brian, got it. Okay, here, I can put the chat where I'll see it. Fine. Good. So now, you know, the next step in the separation of variables technique is we want to divide every term by the product of capital R times capital Y. Okay, so let's do that maybe in red. Okay, so we're going to divide every term by capital R times capital Y. All right, then we can cancel something in most of the terms, okay? So cancel the Y's there, cancel the R's, cancel both of them, cancel both of them. All right, now, what else can we do to simplify this thing? There are too many factors of R squared in the denominator. I'm going to multiply through everything by little r squared. That'll be some level of simplification. Okay, so if we multiply through everything by little r squared, r squared, and r squared, and r squared. Okay. Okay. Now let's see what we have left. Okay. So we now have negative h bar squared over 2m. Okay. So let's see. Our first term is 1 over capital R d by d r squared. Our next term 1 over sine theta d by d theta sine theta dy d theta. Oops, and there's a y in the denominator. Okay. Okay. Now, let's see the third term. 1 over y sine squared theta d2y d phi squared plus r squared v of r is equal to e times r squared. All right, I think I got that right. Close parentheses. Okay, what else can we do to simplify that? Let's multiply through by the thing over here, the negative h bar squared over 2m. All right, so if I do that, let's see, cancel this guy. And so then we have negative 2m over h bar squared. And here, negative 2m over h bar squared. Okay, now I want to classify all of these terms, right? Here we have something like 5 terms, 1, 2, 3, 4, 5, okay? We have 5 terms. Some of them depend on the position, excuse me, on the radial coordinate, little r, okay? Some of them depend on the angles, theta and phi. Okay, so let's figure it out. Let's see if I'll write it in blue, maybe. Okay. This thing depends on little r. This thing depends on theta and phi, but not little r. This thing depends on theta and phi. This term depends on little r. And this term depends on little r. Okay, so maybe let's put all the things that involve little r on one side of the equation, and let's put all the things that involve theta and phi on the other side of the equation. Okay, so if I want the things that depend on little r on the left side of the equation, okay, so first, that is the first term, so that is 1 over the r function, d by dr, r squared, d capital R, d little r, like that, okay? And then minus 2m r squared over h bar squared, v of r. And then we have to move this e term over to the other side of the equation. So I'll put parentheses like this. Okay. So all of this is equal to, what do we have over on the other side? Well, we have negative 1 over y, and then 1 over sine theta d by d theta of sine theta dy d theta plus 1 over sine squared theta the second derivative of y with respect to phi. Okay, now, if we look at the left side, all of this stuff depends on r, not on theta and phi. Right? And if we look on the right side, this stuff depends on theta and phi, not on little r. Now, I can use the standard separation of variables argument and say, how is this possible, right? How can something that doesn't depend on theta and phi equal something that doesn't depend on r, right? How could this possibly happen? The only way is if they're both equal to some constant, right? They both have to be equal to some constant that doesn't depend on any of these three variables, okay? So all of this has to be equal to a constant that is independent of r, theta, and phi. And you see, this argument only worked because of the nice feature that v of r only involves r, not theta and phi, right? If v was more complicated, that would mess up this argument. Okay, so now if we're going to work with this, we need to make a name for the constant, okay? So I will make a name for it, okay? I will call this constant L times L plus 1. Okay, and now you say, why is he choosing such a weird name for the constant? Why not just call it C or something like that, right? And this is a conventional choice, which I am not making up, and you will see that it leads to some simplification in a few minutes, okay? But for now, just think that's a weird choice that I made for the name of the constant. So based on choosing this constant, we now can separate our time-independent Schrodinger equation into two equations, one radial equation and one angular equation. So let's write them out separately. Okay, so first we have the radial equation, which says that this stuff on the left side of the equation equals L times L plus 1. Okay, so I'll recopy that and I will multiply through by this function, capital R, in the denominator. Okay, so this makes that, well, here, let me label that. The radial equation is that d by dr of r squared d capital R d little r minus 2m little r squared over h bar squared b of r minus energy times capital R is equal to L times L plus 1 times this R function, okay? And then there's the angular equation. So the angular equation is that all of this stuff is equal to the L plus 1, And again, we'll multiply through by the capital Y function. Okay, and so what do we get for that? Okay, I guess I'll also multiply through by sine squared theta. Yeah, multiply through by sine squared theta. Okay, so that gives us that sine theta d by d theta of sine theta dy d theta plus the second derivative of y with respect to phi is equal to negative L plus 1 sine squared theta times y of theta and phi. Okay, so this now is our pair of separated equations for the radial coordinate and the two angular coordinates. And one thing that you want to notice about this separation is that this equation, the radial equation, involves V of r, but the angular equation does not involve the potential energy. So for that reason, we, maybe we're interested in lots of potential energy functions, but we only have to solve the angular equation once, right? We don't need to solve it again for every potential energy, right? We only solve it once, and then it works for all V of r functions. Okay, so now I can skip ahead to what is the solution of the angular equation, right? So I'm going to talk about the angular equation for the rest of today, and then the radial one tomorrow. Okay, so to talk about the angular equation, let me tell you things about the solution. Okay, and then you can plug them in and check that these things are really solutions. Okay, so for the solutions of the angular equation, these are a set of functions called spherical harmonics. Okay, which you may have learned about in math classes and maybe in E&M classes, right? These functions are used in E&M a lot also. Okay, so these are functions which have a notation like this. They are written as YLM of theta and phi. Okay, so they are written with two indices, okay, the L and the M. Okay, and conventionally, the L is written as a subscript, the M is written as a superscript. Okay, but the M does not mean a power. Okay, this is not something that's raised to the M power. This is just a label that's written up high instead of down low. Okay, so they are two indices like that, and the rule for these two indices is that L is any integer greater than or equal to 0. and m is any integer from negative L to L. Okay, so you'll notice the L here, this L has to match this L over here, the L that goes in the L times L plus 1. Okay, so this is one reason why I wrote the constant in this funny way with L times L plus 1. The other point I want to emphasize about the L is that it has to be an integer. Okay, it has to be an integer here. That means it has to be an integer here also. Okay, so this equation has solutions if L is an integer. I'll write that maybe here in special color. Okay, it has solutions if L is an integer and not if L isn't an integer. Is an integer greater than or equal to 0, but not if L isn't an integer greater than or equal to 0. So that means that, you know, the product L times L plus 1, right? That could be 0 times 1, that's 0. Or it could be 1 times 2, that's 2. Or it could be 2 times 3, that's 6, right? So there are certain special values that can go here where this is a solvable equation, okay? If you don't have one of those special values, then this is not an equation that can be solved for all theta and phi, right? You could solve it maybe in some little regime, but then if you tried to extend it all the way around the globe, it would conflict with itself and wouldn't find. So there are only certain special values of the constant which can go there to make something that has a consistent solution that works everywhere around the globe for all longitude and all latitude going over the North Pole and the South Pole. Okay. All right. So you have an equation like this, not an equation like this. You have this equation. Okay. You have this equation with one of the special values of the constant, like 0 or 2 or 6. Okay. If you have one of the special values of the constant, then you get a set of solutions. If you have a constant here that's not one of those special values, bummer, you don't get a solution that works all the way around the globe. So if you have one of those special values of L, then you get the solutions YLM. Okay, so the L here has to match the special constant that you have. And then the M here can be any integer from negative L up to L. Okay. So this then makes a set of special functions that we can work with for solving problems in spherical coordinates. Let me tell you a few things about these special functions, and then I'll switch to Mathematica and show you stuff about them. So let me tell you special things about spherical harmonics. Okay, spherical harmonics. I guess the first thing I want to emphasize is that, in this class, we cover a lot of different kinds of special functions. And so we did Hermite polynomials already when we were talking about the harmonic oscillator, and there are a whole bunch more coming, okay? But of all the special functions that I'm going to talk about this semester, the spherical harmonics are the most important. And these are ones that are actually worth learning, okay? So worth learning about. And they are useful in several areas of physics. They are not just useful in quantum mechanics. So it's quantum mechanics, they're useful in electricity and magnetism. You might have already seen them there. I work in liquid crystal physics, and they're sometimes useful in liquid crystal physics. They could be even useful, say, in geology in a way that I'll show you in a minute. Okay? So these are actually very broadly applicable, the way that sines and cosines are very broadly applicable. And indeed, I'll make an analogy, like an analogy that you would see on the SAT or ACT or standardized tests like that, right? We could say spherical harmonics are to a sphere as sines and cosines are to a circle. Right? So this is like scaling up from a circle to a sphere, right? A sphere is like the 3D generalization of a circle, right? And the spherical harmonics are a 3D generalization of sines and cosines, in that they show all the ways that a function can depend on orientation, can depend on angle in 3D. Right. So on which way something can depend on latitude and longitude. And so we could say for small L and M, they show gradual variations. On the sphere. And for large L and M, they show sharp variations. And in that respect, they are like sines and cosines, right? Because if you have a sine of M phi, if M is small, this gradually varies as a function of phi. And if M is large, it goes up and down really rapidly, something like that, right? And so it's the same kind of thing with spherical harmonics. We've talked a lot about orthonormal functions in this semester, and these are indeed an orthonormal set of complex functions. So that means if you do an integral over theta and phi, so an integral from 0 to pi sine theta d theta an integral from 0 to 2 pi d phi of one spherical harmonic, so YLM of theta and phi, complex conjugate, times another spherical harmonic, YL prime M prime of theta and phi. This integral is the Kronecker delta, LL prime, times the Kronecker delta of, M prime, okay? So this integral is 1 if L equals L prime and M equals M prime and 0 otherwise. And you'll notice when I did this, I remembered to put the measure of integration right there for theta. I don't need that for R, but I do need it for theta because there's an angular integral in here. Okay, so these are general points about these functions, but now, if you haven't seen them before, maybe you're wondering, what are these functions? So I'll write a few of them for you. So for examples, all right, well, we could do for L equals 0, M equals 0. This function is a constant. It is simply 1 over the square root of 4 pi. That's sort of boring. How about if L equals 1 and M equals 0? Then we have the square root of 3 over 4 pi times the cosine of theta. What if we have L equals 1 and M equals plus or minus 1? Okay. Then we have minus or plus the square root of 3 over 8 pi times sine theta e to the plus or minus I phi. Okay, so these are a few examples of the spherical harmonics, et cetera, et cetera. There are more written out in your quantum textbook, and also, I assume, in your math textbooks. Let me show you some things about them in Mathematica. That would be maybe more interesting. So if I switch to Mathematica, I stop the iPad and okay, so if I want to go to share, good, you got that, right? Yes, good. Okay. First of all, this is the Mathematica notation. Okay, so in Mathematica, Wolfram Company made its own notations for spherical harmonics, and so their function name is spherical harmonic Y. Okay, with capital S, capital H, capital Y, right? And then it's a function of 4 arguments. The first thing is L, the second is M, the third is theta, and the fourth is phi. So now we can tell Mathematica to evaluate it. Mathematica knows these things, okay? So the spherical harmonic 0, 0 is a constant. I wrote it as 1 over the square root of 4 pi, but here Mathematica has simplified that square root, so factored out for 2. Okay, what about here? If L equals 1, then we can have the index M is -1 or 0 or +1. If L equals 2, we can have the index M is -2, -1, 0, 1, or 2. Okay, and it keeps going up from there, right? So I could say spherical harmonic y of 10, 10 of theta and phi. And so, okay, there's a function that is a more complicated function, right? So this is the y1010 function. What do these things look like? Okay. So we can plot each of these spherical harmonics. So, we need a way to plot functions of theta and phi. One conventional way is by making what Mathematica calls a spherical plot. Okay, so that means a plot where it draws a surface with the distance out from the origin is equal to the value of the function that we want to plot. Okay, so if I want to say a spherical plot 3D of the spherical harmonic, if I do the 0, 0 spherical harmonic as a function of theta and phi, and I could tell it, make this plot for theta goes from 0 to pi and phi goes from 0 to 2 pi. Okay, so this plot just looks like a sphere because the spherical harmonic 0, 0 is just a constant. Okay, so it's drawing a sphere, and the radius of this sphere is 1 over the square root of 4 pi. What about if I want to do this kind of a plot for a higher order, more interesting case? Okay, so suppose I want to do the spherical harmonic 1, -1. Okay, so L equals 1, M equals -1. Okay, it does nothing. Why not? Right? Aha, I made a mistake. Okay, my mistake is the spherical harmonic 1, -1 is a complex number. Right? If I look at this function, oh man, it's a complex number. If I tell Mathematica to make a plot of a complex number where it's expecting a real number, it gives up. It says, I don't know what you want me to do. I'll just leave it blank, right? I have to tell Mathematica a real thing to go in here. So I could either tell it to plot the real part, or I could tell it to plot the imaginary part, or I could tell it to plot the absolute magnitude, right? But I have to give it something real to go in here. How about if I tell it, plot the real part? Much better. Okay, so this then, for the spherical harmonic with L equals 1, this is actually still a sphere, but I'll point out something really tricky. It's a sphere that's been displaced over. The center of the sphere is not at the origin, because here, this is x equals 0 is way over here. So this is a sphere that is displaced in x. And likewise, if I make the spherical harmonic plot of y 1, 0, so L equals 1, M equals 0, this is a sphere that is displaced upwards in z. This is a very surprising feature associated with the L equals 1 spherical harmonics, that the plot is just spaced somewhere like that. What if we go to higher order? What if we have like L equals 2? So here is a plot for the spherical harmonic with L equals 2 and M equals 0. So this is something that has multiple lobes, you could say, going upwards. And each of these lobes is symmetric about the z-axis, right? You can rotate about the z-axis and it all comes out looking the same. That goes along with m equals 0, having this rotational symmetry about the z-axis. Okay. What about L equals 2, M equals 1? That is a plot like this one, right? It also has the multiple lobes, and now it has lost the symmetry about the z-axis. Okay. What about L equals 2, M equals 2? It has these multiple lobes, and now they're arranged differently, right? That now they're arranged around the z-axis like this. Okay. What if we go up to M equals 3? Well, it becomes less symmetric, right? You get this kind of a structure where plus z and negative z are not equivalent to each other. Okay. That's characteristic of the odd L's, so that they are different for positive and negative z. And then you could also make something with more like threefold symmetry, like this. Right? This is L equals 3, M equals 1. Here's L equals 3, M equals 2. It's more like a tetrahedron, right, with 4 lobes sticking in different directions. Here is L equals 3, M equals 3. Okay. So this is something where there are 3 lobes sticking kind of symmetrically out around in the XY plane. Now you might be wondering, what's so special about plotting the real part? Should I maybe be plotting the imaginary part or the absolute value instead? Just for comparison, here's a plot of the real part for the y2, 1 function. Here's a plot of the imaginary part. Okay, so it shows very similar features. It's kind of rotated around, but there's a real and imaginary part of these functions, and they can be rotations of each other. And the absolute value squared then looks like this. Okay, and so that gets some extra symmetry. Okay, hey, I'm running out of time now. I mistimed this because I still have more Mathematica stuff to show you. Well, I'll save it for tomorrow. Okay, I'll show you more Mathematica stuff, and that'll be the beginning tomorrow. And then we can continue on with other things. Okay, so I'll break for here and answer questions if you have any, and then we can continue on same time tomorrow. All right, thank you guys. See you then.